A koala?
Yeah.
It depends on my ability to find a koala. Get out of here, koala. Okay, we'll see what's in there by Sunday. Anyway, I'll have these up by Sunday. As always, let's review. So again, remember today's double lecture. And I will let you know when I will not have any more material on the exam. And that probably will not be today. Probably we're going to go to Monday. Probably material even covered on Monday will be on the exam. I'll let you know. I haven't written the thing yet. Anyway, okay. So let's review what we did last time. Now remember, don't forget this. And of course I'm going to beat you to death over it on homework questions. But remember that when you have a gas expands, a gas contracts, a fair amount of this test, second test, a lot of it, and also you'll see it on the final. A gas expands, a gas contracts. You're going to see 4 possibilities: adiabatic, reversible, irreversible, isothermal, reversible, irreversible. Those are 4 conditions, right? Those dictate how you answer the question. And so unfortunately, there's a little bit of a memorization component to this. But as we work through this, we're just now getting through how to calculate all the variables. And what I'm going to do, especially for the second part, where we're going to kind of be doing this over and over again, I have ways to help you, like mnemonics, to remember how to keep it straight, what equation is for what condition. So I'll make that as easy as possible. And you know, I don't like content that's just based on memorization. At the same time, I can't have it in class that's free of that either. This is just not possible. Okay, so we did isothermal. Remember, isothermal, irreversible is very easy. Irreversible is easy. Reversible is a little bit more difficult because of the work equation. Adiabatic, I showed you how you ultimately have to get the change in temperature. Sorry. Actually, before you do anything with adiabatic, you always write this first. Immediate point. Adiabatic is thermally insulated. There's no heat exchange. And that means that we're going to be, let's say, compressing a gas. And of course it gets hot, and before it used to shed its heat to be isothermal, but now it won't. So there's going to be a temperature change. All right, you've written this down, but everything else, answering all the other variables, give me delta U, give me delta H, you have to get the temperature change. And we talked about how U is exact, and we can equate the work to the temperature change. That's how we get the temperature change. In an irreversible case, you just integrate both sides. I showed you, I know that looks like it's easy. It really isn't, because it's a calculator nightmare, and that's irreversible. Reversible, we had, we note that the exterior, this is reversible. Exterior pressure is constant and irreversible, and you just integrate it. In reversible case, the exterior pressure is equal to the interior. So it's hiding a V and a T. So you have to take that to account and integrate, and you get this equation again. This is just reviewing from last time, so I'm not skipping over some horrendous derivation, just reminding you. And with this now, of course, I've given you all the information you need except TF. You get TF. Then you can calculate the change in U. With TF, the change in U will be CV delta T. Look out for CV. Remember, I'm going to give you the per molar, because that's something that can be tabulated and expressed easily, obviously. So multiply that, here. Let me just, why am I babbling? Do this. Okay, the per molar multiplied by moles in delta T, and then the change in H is, again, what, I just did it again, right? I'll either give you the heat capacity at constant pressure per mole. There you go. And that's all we've gotten so far. The work, this is equal to the work, because delta Q is 0. And there you go, we've gotten them all. Although we're going to be introducing some more variables. We're going to be introducing entropy maybe today. So we might actually have another thermodynamic variable to calculate. You see, it's kind of piling up. This is why it really will get a little painful, but again, I'll help you keep it straight. Okay, another thing to be wary of in adiabatic. Now remember that, now be careful of what I'm going to draw. Don't let yourself get lost in your notes. When we're doing isothermal, and let's do an expansion. Expansions are kind of easy for this. You know, for isothermal, that pressure was proportional 1 over V. That was like Boyle's law or whatever. And that's very easy. It's basically a 1 over X type curve. That's what I'm trying to draw. If you're doing adiabatic PV isotherms, wait a minute, what did I just say? An isotherm, you can't do an isotherm. There are no isotherms if you're doing thermally insulated systems because temperature is automatically changing. Now again, I drew an expansion. So let me do an expansion but adiabatic, and I'll start at the same spot. What you get, and you figure that out using this, is it's similar but not quite the same, not quite the same. That is not an isotherm, that is an adiabat. I like that, it sounds like a bat. Maybe there's a bat in here, it depends whether anyway, you'll see. Okay, so that is an adiabat. Let me, maybe I'll draw a little equal sign there so you don't get confused. Okay, isotherms, adiabats. Now, adiabats drop pressure. All right, so you're expanding, and the pressure's dropping more than it should. Now, of course, by should I mean if you're an isotherm. Why would pressure drop in an expansion? Okay, give me a simple reason.
Volume makes sense.
Volume pressure goes up.
Well, okay, now volume increases, pressure decreases, that's true, but why does an adiabat drop further? It's still kind of 1 over X looking, but it drops a little more than it should. But so why did it drop a little bit? Of course it went down, but why?
Because the change in heat is not equaling the work. Change in temperature.
The change in temperature, the temperature is higher?
Lower.
Lower, right, it cooled, right? You see, the temperature dropped because it cooled. PV equals nRT still works, it's just that PV and T are simultaneously changing. Remember, that's why we get into this, a little bit of nastiness to begin with. Remember that I figured all this out with PV and T all simultaneously changing, that's why I needed 2 equations to solve for that. Okay, now again, this is just a reminder. The purpose of adiabatic transitions is, for one, things are thermally insulated like a refrigerator, so you need to know about stuff like that. But when it comes to understanding the fundamentals of thermodynamics, it turns out that these characters back in 1880s, they built these crazy little contraptions, little mousetraps, and they used adiabatic systems quite a bit, and they did this to test their knowledge of thermodynamics, which is what we're doing today. And I also valued last time about how, like, it was on your homework, how heat capacities are almost described by the heat capacity constant volume. It's the derivative of U with respect to T. U is defined by the equipartition theorem, so like nitrogen should have 5 halves R, and it is. But if you look out to like 4 or 5 significant figures, all of a sudden it's a little off, right? And that's not, you know, and I told you in PChem, it is or it isn't. And then if you looked at, what did it have, acetone, maybe some of you looked at the other question, peroxide, then all of a sudden the differences really could get, there could be actually big differences. So these equations don't work that well. Well, why not, right? So what is, if this is only sort of correct, then it's really not correct. So what is correct? I'm going to explain that today. Anyway, and I even hinted a little bit about that, but let me more formally introduce these 1880s types of experiments, really kind of funny contraptions that James Joule and Thomson, I forgot his first name anyway, Kelvin, Lord Kelvin, these two get together at a meeting when James Joule is telling people that he thinks he can turn heat to work. I mean, swear to God, I'm turning work to heat, but they didn't believe that. I don't get that. But anyway, it took James Joule a little convincing of people to believe that. Kelvin was one of the first people that believed, they supposedly argued quite a bit. And so once they figure out work can turn into heat, they basically figured out the first law of thermo. And then they started building contraptions together. James Joule was fairly wealthy, so he wasn't working. They built these giant contraptions to test thermo. And a lot of times they needed really accurate results. And a lot of times things work better if they're bigger. So it's thought that some of these contraptions I'm about to draw were as big as houses, but they were also obscenely dangerous, so they didn't tell anyone that they were doing it. So that means people aren't really sure about this, but they think back in the 1880s that James Joule basically gutted a house and built these giant, obscenely dangerous machines to make measurements on liquefied gases and whatnot. And they reported their results, but no one really knows exactly what they did. So anyway, I thought that was a little historical funniness. It's something I would do, especially the explosion part. Okay, so we start with Jules Experiment. There's 2 of these. Jules Experiment. And again, these are all like 1880s or something like that. And I hinted a little bit about this on the homework, and that was a reason for this. What we have is a vessel with a gas connected to a much larger one. And I was even talking to some of you earlier that, the larger one is going to be under vacuum. And of course, we're going to expand the gas into that vacuum. And we're just going to say that the vacuum maintains a vacuum even when the gas expands into it, which is a bit of an approximation. Okay, and that little drawing I have in the textbook of this, maybe some of you recall that. That's my best Photoshop Illustrator skills. So there's water in it. It's in a water bath. That is how they did it. It is thermally insulated. Of course, they have a temperature. And so there you go. That's how they did this. It actually, I went through a couple of figures before maybe if you know the book, if you are reading along, I figured I could put like cutaways. Hopefully that came across well. So of course this is glass, wool, or just write down that the system's adiabatic. Okay, if I say it's adiabatic, you should immediately write down that there's no heat transaction. Okay, 1 point. There you go. Okay, so again, big picture. These 2 characters are trying to test their knowledge of thermodynamics. Remember, they discovered all this, a lot of this. We're actually getting into entropy, and that was another person. And between James Joule, Kelvin, and this guy named Sadie Carnot, that's basically everything that we're covering. So anyway, all right, so they built this contraption. Why? Okay, now you know the gas, if you expand the gas to the vacuum, is it going to get hot or cold? Cold. And I've got a water bath. Now, of course, that'll kind of dilute the coldness. And then I've got a thermometer, right? Yeah. So this is kind of cool because that's not going to work out. And so this is why they built these really, this is way more complicated than it seems. So let me walk you through it. It's kind of cool that they thought to do this. Okay. So adiabatic, so the whole system, it's like a system in a system, and that's part of the cleverness. But we have to stand back and look at the whole thing. And it's just a giant thing wrapped in glass wool. It's adiabatic. Okay, what about the work? And now, of course, as a purist, I have to define the work as exterior pressure. Okay, what's the work going on in here? Right, 0. Now again, if you expand the gas into the vacuum starts to pressurize, so this is a little bit iffy, but it worked pretty well if you had a really small volume and a really big container. And maybe that's why they built these as big as houses, right? So, yes, so there's no work. Okay, so now think about this. If there's no heat and no work, what's the change in U? Right. Okay, now, we've been doing reversible, irreversible, constant pressure, constant volume. We've done constant temperature, constant internal energy. See, what a crazy thing. What they're doing is they're trying to, they're going to look at a temperature change as a change in volume. Because they built the thing, they knew what the volumes were. It's kind of easier to think of it as a change in volume. But what's held constant? The damnedest thing, they built something that held internal energy constant. That's so weird, but they did it. And I mean, it's not that hard to figure out, right? So there you go. All right, now, so what did they measure? Thermoproof. This is what you're going to have to start getting used to. And on the homework, I have you do a little proof where I think you do basically what I'm about to do with enthalpy, something like that. Anyway, so what do they measure? Let's predict with a thermoproof. And now, again, whenever I have you do this homework or exams, I'll always give you a starting point because remember I said we have 12 variables, right? 12 variables, you could write the change in any one of them, and you would actually get to the right answer. It's just a matter of steps. All of this is self-consistent, so if you start doing a proof, you will get to the right answer no matter how you begin the proof. It's just a matter of steps. I happen to know what are the fastest number of steps, right? So I'm going to start that way, and it just makes it easier for you. Now, despite the fact that u is held constant, I'm actually going to start writing the change in u. I'm going to begin my proof to try to figure out what this is by writing down the change in u. Now, you have to have it in your head, as I emphasized on the first Friday, change in f is change in f, change in x times change in x plus change in f, change in y, change in y. Right? You always have to see all of this that way. But I'm not gonna write that down because I don't have room or time. And what we're gonna do is we're gonna let volume change. There we go. Now, we always see volume and u together. They always seem to come together. That's probably because the change in work is the change in u. So v is one of these natural variables. So I always see those two coming together. Whenever I see a v, I'm already thinking, you know, that's one reason I started with the change in u, because I saw a change in v. And v and u always go together. Okay, now the next thing is to note that, again, I happen to know how to do this the easiest way. So I'm going to hold temperature fixed on the first little change, and then now I am obliged to let temperature change. Of course, then I hold v constant. There you go. Now, here's a funny thing. Again, I could set this up. I could have held, I could have held anything else constant. And I would eventually get to this. It's just a matter of steps. I just happen to know that the next thing I want to change, I want to let volume change, and then I want temperature change. I just know that that's the best way to do this. Now, it turns out that temperature, by the way, and don't write this down, don't even remember this. Volume is the natural, one of u's natural variables, but temperature isn't. I can still do this, it's fine, but I just want to point out to you that temperature is not the thing for internal energy. That actually is entropy. We haven't gotten there yet. It doesn't matter though. We can write anything we want. Okay, so next thing, let's see. I can go ahead and simplify this. I'm going to just say du dv, a constant t, dv. And the thing is that I happen to know that the du dt at constant v. Now I don't want you trying to, I'm telling you, I don't want you to try to memorize too much stuff, but I don't know. You might want to remember that. The equation, that's on the cheat sheet on the exam, by the way. Du dv a constant, wait. Yeah, right here. The u dt a constant v is cv. Sorry, see what I just did? That was stupid. Okay. All right, now let's see. I am trying to get to dt dv. So I need to turn this, I need to find this in here. And I can see that I got a dt on top. So what I'm thinking is, let me rewrite that. Du dv, constant t, dv. Okay, I see that I got a dt right here. And what I need is the change in volume. And remember, I can do anything I want. And now I'm going to hold u constant. Again, anything goes. It's fine. There we go. All right, so notice that I've now found the thing I'm looking for right there. So now it's all just a matter of algebraic simplification. dv is 1. Okay, what's the change in u when u is held constant? Right, it's a over b when a is 0. That's 0. You can think of it just like that. Okay. I hate to do this, but let me put cv dt dv on the left, because we, in our Western civilization, we like to read and write from left to right. There we go. And therefore, this quantity, which, by the way, has a special name, it's given the symbology, little micro symbol with a little j there. That's the Joule coefficient. And it turns out it is equal to 1 over CV. minus 1 over CV, change in U, change in volume with respect to T. Okay, so there you go. Did I get that right? Yeah. I was actually doing this without my notes, which is always scary. That minus sign is not perfect and it bothers me. The world will explode if I don't get it just right. There we go. That's nice. Okay, so what do you think they measured? Did it get cold? Or did they not measure anything? It got hot? Did the expanding gas get hot, cold, or really nothing happened? Changing U at constant T. The effect, so volume went up plus divided, and on top. So you got a plus on the bottom. If the top is plus or minus, determines what you get. It's equal to this jazz. I see a minus sign. CV is positive. The UDV at constant T. Now, it depends whether that's positive or negative. Or zero. What do you think? Zero? Why?
Because U isn't changing.
U is that? Right. Constant temperature. What's the change? Isothermal change in U is? Yes-ish. Yes-ish. That's mostly correct. 91%. For a perfect gas, the change in U is 0. For a perfect gas, the change in U is 0. Let's also get our units. So they measured, Joule and Kelvin actually got no temperature change. Later in 1924, somebody else came along and did a much more sophisticated experiment and found a slight temperature change. Anyway, and I'll get to that in a second. I like to get the units right, and that would be Kelvin over meters cubed. And I can either say that I'm looking at that, or I can see that it's equal to Kelvin over meters cubed. Look over there. Okay, hold on, let's do this one. Okay, meters cubed comes from volume. Energy over energy per Kelvin is Kelvin on top. There we go. Okay, so they mostly got 0. So again, this was so clever. Yes, an expanding gas cools, but not in this machine. In this machine, because of the weirdness of expanding into a vacuum and wrapping the whole thing in glass wool, they actually saw no temperature change whatsoever. Now again, it's not that it's 0, it's just really close to 0. And it's because the change in U for a perfect gas, there's no change in U for a perfect gas.
So is the Joule coefficient a really small number?
So, yeah, right, sorry. So, yeah, they're really small numbers. So let me get into that. Now let me tell you what's in the future. Right now, I said this last time, a lot of what I'm covering is a simplification and is not quite right. It's just a good starting point. Now, in about 2 weeks, we're going to actually revisit this, and you're going to, even on your homeworks, you're going to do derivations. You're going to have to use van der Waals equation, by the way. When you revisit this with a better thermodynamic toolkit, and you use the van der Waals, you're going to find that this is not equal to 0. That's coming later. For now, a perfect gas is 0 for all the reasons we just said. And so there you go. That's really all I've got. But because, as I've been valuing, this is not quite 0, let me explain why. And again, understand that you will see this again, and then you're going to be able to put like numbers to pen and paper. Not today, though. I'm just kind of trying to introduce all this. And I would struggle with this. Should I introduce this now when I'm still teaching approximations, or should I wait once we've covered entropy, and then you can do it for real? Well, I've made my decision, so here we are. But once we get a little further along, and then again, you can do those derivations, and you'll find that the Joule coefficient is close to 0, but not quite 0. Here's how that's going to work. So, let's say that we're at a constant temperature, and what I'm doing is I'm looking at the internal energy of a gas as I change the volume of the container it's in. Now you should know that what's happening for a perfect gas, nothing changes because perfect gases don't interact with each other. I could bunch them up to the right next to each other. I guess that's actually a solid, but anyway, I could bunch them up to the right next to each other, and a perfect gas doesn't care because they have no volume, no B parameter, and they have no A parameter, so they don't attract either. Remember, B's are like collisions, and A's are more, attractive type interactions. Okay, so perfect gas doesn't care. But gases aren't perfect gases. Nitrogen's close, right? The nitrogen's A and B perimeter kind of cancel each other out. You did a homework on that. Okay, let me show you what most gases do. Most gases like each other. And they work like that. So at large volumes where they're not interacting, gases will behave more like perfect gases. Real gases behave more like perfect gases at high volume because they're very far apart from each other. But when they're close up, they give each other a little kiss. Like, anyway, so this is most gases. And they like each other. That means that the A parameter kind of dominates over the B. Okay. There are some gases that don't like each other. These are unusual. In fact, I can only think of 3 of them. They're the haters. And that is helium, hydrogen, and what's the other one I keep forgetting? Neon? What's the top of the Nobel? Neon, right?
Neon.
Yeah, neon. Only those 2, and those are collision oriented. They're always hitting each other. And they're just not big enough. Remember I talked about how the A parameter is kind of a polarizability thing, and you have to be big and fluffy like xenon to have a good A parameter. And if you're like a little small like helium, then you have you're not attracted to each other, and so you're more colliding than attracting. Okay, so that makes it a hater, and that means that the internal energy rises with proximity. Okay, now let's look back at this. Now again, okay, Joule and Kelvin, despite having equipment as big as a house which scared the heck out of everyone, they did not measure a temperature change, but later someone came along with much better equipment and they did see a finite temperature change. But was it positive or negative? Okay, so now you should be able to look at a graph and understand that this is a slope. You know that slopes are positive or negative, and you can tell me whether this is positive or negative, and you know if V goes up, whether T goes up or down. Okay, that's what I'm walking you through, right? So, because I'm probably going to put something like this on the exam, because you should be able to do this. You're almost college graduates. Okay, let's do most gases, right? Because most gases are most gases. dV, du, dV. I'm doing the slower one. Positive or negative? Positive. Right, okay. Okay. Negative, positive is? Negative. Okay, if volume goes up, this is positive, T is? Negative. Right, okay, follow again. Everything's positive except there's a minus sign. That makes us negative. Again, these partials are like A over B. If the change in volume is positive, then that's B. Then the A, the thing on top, has to be negative for it to be negative. That means that the change in T is negative. That means that when I deleted it, but when they expanded the gas, it got cold. But what happens if you expand helium? It gets hot, swear to God. Right, so that's negative. So negative, positive. That means if volume goes up, temperature goes up. Swear to God, an expanding gas gets hot. That's like you're outside. If we lived in a helium world, if you're outside, there's a breeze, you burn up. Literally, that's what would happen. So I always thought that was kind of funny. Now again, I want to point out that you should be able to follow through with this. This is a question a question like this I frequently have on exams, and you should just be able to do this stuff. And again, I want to point out that we're going to revisit this problem. So again, I never know whether I should introduce this now. But later, you're going to be able to expand this derivation. You're going to be able to expand it with the van der Waals equation, and then you're going to find exactly what's the innards of the Joule coefficient, and you're going to find it's very close to 0, but not actually 0. Okay, now they did a second one of these, and this one's important because this is how they figured out how to refrigerate, how to make refrigerators. And they also tried to liquefy gases. Apparently, Joule and Kelvin were going nuts. They were trying, back in the day, right, they're still riding horses. And they almost were able to liquefy gases. It was like hypothetical that you could liquefy a gas. People thought it was possible, but they weren't totally sure. And liquefied gases are like hideously important. I know that if there's like any power difficulties in your local area, we get notifications. You know, if the power goes out, we get notifications from the gas companies that they write to us. They're like, look, if you have an order in, you're going to be waiting because we go to the hospitals first. And I'm like, what does a hospital need with liquid nitrogen? I don't know, but I don't think they're doing anything evil there. So I'm glad that they get that. So liquid oxygen, liquid nitrogen, liquefying gases is a very, very important thing to our society. MRIs use liquid helium, right? So anyway, the next thing they did, which is called the Joule-Thomson Experiment, although they weren't quite able to do it, someone came along right after them, and I forgot that person's name, and was able to build a Joule-Thomson device big enough to liquefy air, and that's what we've used ever since. Okay, again, so Joule and Thomson built a bigger mousetrap, and it's funny that a lot of people put Joule-Thomson's name, but it's not. It's like a common mistake. Okay, now if you can imagine, we've done volume, so let's do pressure instead. All right, so they tried to do the same thing, but they wanted to do it with pressure this time, and they're trying to not observe zero. Right, that was their goal. And by the way, again, that is how you're going to liquefy. That's how you're going to liquefy gas. Okay, and what do you think I should hold constant? Now, if I have pressure, now when I see volume, I always see internal energy. I said that like a zillion times. If I see pressure, I always see what? Enthalpy. Enthalpy goes with pressure, internal energy goes with volume. They're always hand in hand. How in God's name do you build a constant enthalpy device? This is one of the wackiest things I had ever seen. What a question. Well, here, let me draw it. So, and I have it in your, it's called a throttle, by the way. Ha! Now I feel superior. So, this is one of the craziest devices, and to prove its constant enthalpy is like, it took me when I was writing the book, it took me like 5 tries to get this right. This really isn't hard, but anyway, you'll see. Okay, so let me draw it. Now, in the textbook, I think I did really an infinitely better job. Well, because I had Illustrator. I've gotten pretty good at Illustrator over time. Okay, now, of course, we've got a cylinder body, and we've got a piston. And again, I may not say too much while I'm drawing this, which is always a little awkward. I try not to be too awkward. Can't help it. Okay, so there's a piston. There we go. I've got to get the perspective right. It's horribly important. Okay, now here's the valve, throttle, by the way. So it's a little disc. So again, they did call it a throttle. Let me write that down. And then next to the throttle is another piston head. And, well, it's just a piston. Okay. There we go. And I've got to remember that. Like that. I gotta remember, get the perspective just right. All right, there we go. Do that right? No, that's weird. No, that's weird. There we go. It's got to be perfect, or the world will blow up. Okay, now the throttle turns out that it's just a porous plug, like a zeolite. Have you guys heard of zeolites before? I'm always surprised. I knew what a zeolite was when I was your age, and I'm just kind of finding it odd that you folks don't. Someone just didn't tell you about zeolites. Zeolites are kind of cool. They're minerals that are very porous. They're silicates, so it's sand is SiO2, but if you mix in sand with just a little bit of some magnesium or something, they can form really complex three-dimensional structures. And now one of the bigger reasons I'm surprised, because they're very porous, they allow gases to go into them, they're easy to put metals into them like catalysts. Guess what industry uses them? Begins with an oil.
Petroleum.
The oil industry. Oil industry is the biggest consumer of catalysts. That's how they make their catalysts. You make these by the megaton, throw them into the reactors, take the oil, heat it up to beyond belief, and you get rid of all those pesky double bonds that are really bad for fuel. Anyway, so a throttle can be something that's very porous. What that does is the purpose of it, and don't worry about like trying to memorize, don't memorize this, I'm just telling you about this, it's not that important. When gases, what's going to happen is we're going to take gas in this part, we're going to push it into that throttle at constant pressure. Now that's work, but when the gas goes through the throttle, it's like here's these gas molecules and they're approaching this throttle, this zeolite. They go into it and they get kind of randomized, then they come out to the other side. And so what we're going to do is we're going to completely close the right-hand side. We're going to completely close the right-hand side and expand the left-hand side. There we go. Actually, what I'm going a little nuts over here is I'm making sure that the perspectives are correct because I do that. There we go. Okay, so there's the other piston. Now what I'm trying to draw here is that this piston is now touching the throttle. So what I've done is, that means we're at P2, V2, T2 here on the right. So what I've done is I've completely pushed the left side, I've completely pushed the gas through all the way to the right side with the throttle being in between. And it's wrapped in glass wool. Wrapped in glass wool. Okay. I'm just going to write adiabatic. Okay, so that's the mousetrap. Sorry it takes me so long to explain it. I want to see if I can, I'm sure someone has built one of these. In fact, I know that they built one of these. I was trying to see if I could find one and bring it to class, but it turns out they're complicated enough that they actually use them in labs, so it didn't really make sense to try to buy one of these. Okay, so what? So what about this? Okay, so this is constant enthalpy. The genius of this, though, is that the initial state is here on side 1, but on side 2 there's nothing. Everything is 0. There's obviously no volume, there's no pressure, there's no moles. Now here's the genius part. That means that there's no internal energy. The initial internal energy is 0. And then on the left side, after the transition, there's no pressure, no volume, no gas in the left side, so its final internal energy is 0. So the initial internal energy on the right is 0, the final internal energy on the left is 0. That's why this is so clever, and they do that by having no gas present. Now that allows me to do this, calculate the change in U. Change in U is going to be the change in the left and the change in the right side. So make some notes on that because I can't really write all that out. And this is the kind of thing that you can get confused by your own notes. Now don't forget that this will also have to be equal to work because it's adiabatic. There is constant, there's compression and expansion against constant pressure. So there's work being done. There's no heat transaction because it's adiabatic. Okay, regardless, let me do the U's first because this is where this gets clever. Okay, let's do the change in U. U1. Okay, the final state here on the left side is 0 because there's no gas there. The initial state, remember final minus initial, we'll just call it U1. Right? P1, V1, T1, U1. Okay? Now, I told you this is how it's clever. The final internal energy on the right side is just U2. The initial internal energy is 0 because there's nothing there. Right? So that's clever. Okay? And this is equal to U2 minus U1. Clever. Okay. Now this is equal to the work. And these will be constant pressure works, right? Now you can see why the porous plug is really clever. Because you can keep pushing on it without the pressure increasing. Right? Because it lets the gas bleed through. That's why that's clever. Okay, so let's, and you're going to see this clever initial final thing as well. And then we'll break there. Okay, how does that work? So the initial volume is V1. We're going to do the right side, V1, but it ends at 0. And of course, it's at pressure P1, and that's constant. I can take it out. And then we're just going to add to that to the right side. Energies just add. The initial volume is 0. The final volume is V2. instead of constant P2. Okay, let's see what that ends up equaling. That ends up being minus P1, 0 minus V1. Okay, and the world's most simple plus, oh no, not plus, minus P2. The V2 minus 0. Oh, sorry, I forgot units, but I don't want to, I'm kind of out of time here. And what does that end up being? That ends up being P1 V1 minus P2 V2. Kind of clever how I wrote it all out. Yeah, it's probably hard to follow in your notes, but maybe watch the video again. Okay, then I can do some rearranging. Let's see, I'll bring P2 V2 onto the right. So I've got U2 plus P2 V2 equal to U1 plus P1 V1. Ta-da! You see what I did? Enthalpy on the left is equal to enthalpy on the right. And that's final initial. So again, crappy board. That's the same thing as H final. Because remember that the second state represents the final state because there's nothing in the right half is the final state because the left half is empty. H initial, and therefore delta H is 0 joules. So that's how they do it. It's very, very clever. Okay, in the last bit of time I have, I do want to show what that means. And what we're going to do is calculate the change. We're going to do this. Now, at this point, I'm going to blow through this because this is hopefully quite easy. And I have a bunch of, practices on the homework. We're going to do dH dt at constant T, dt. And again, I happen to know, of course, I want to do H. And now, don't forget this. If I tell you that P is constant on the first term, you really have to let it change on the second term. It's not fair. Okay. Then what I do is I'm going to, let's see, I've got the change in T, so I'm going to want to divide by the change in P. Change in P. Let's see, and then I'm going to hold H constant. And let's see, am I doing that right? Okay, so this, of course, is 1. This, of course, is 0. And now I've got the change in H. What have I got? I've got, sorry, I'm kind of blanking out here. Oh, that's CP. CP, constant H. And that's what I'm looking for. Plus the H, dP, constant T. And now I have to do some rearrangement. I have to say dt. So I'm going to blow through some algebra because I'm kind of out of time. Okay, and this, of course, will be the Joule-Thomson Coefficient. Again, we're changing the pressure. We're looking for the temperature change. And this ends up being, let me check my nose case. Basically, it looks almost identical. Except there's H's where there were U's, and there's P's where there were D's. And as before, what do you think? It's close to 0. Close to 0. And that would be Kelvin per, these are usually in kelvins per atmosphere. So I'll put atmosphere. So you can look these up, by the way. Kelvins per atmosphere. So again, clever mousetrap. Adiabatic, iso-enthalpic, mostly because of this weird throttle deal. This is a very weird derivation. Hopefully I made it seem easy, but I swear to God, if you try to do this from scratch like I did when I wrote the textbook, it's a nightmare. Same derivation, and we again find that there's actually a very slight, it's not a big effect. So again, most gases, of course, if you depressurize, the temperature will go down. Most gases will do that. Now here's the thing, and I don't quite understand this. This is bigger than the Joule. This works better than the Joule system. I don't know why, it just does. And because of that, because this works better, eventually, we were able to liquefy gases using this thing, and this is the basis of modern refrigeration. And again, when we revisit this, you're going to be able to do derivations with like the Van der Waals equation, and you're going to show that the Joule-Thomson coefficient, which will be related to like A and B parameters of the Van der Waals, is close to 0, but not quite 0. Okay, I've gone over 10-minute break, and we got to talk a little bit more about Joule-Thomson, and then we're going to introduce entropy. And turn in your homework if you haven't done so, and 10-minute break.